But with our polygons, or with our vectors in general, this example is just showing how we can encode information to store polygons, and going from polygons to networks and networks to polygons. What does that mean? Well, we have some form of direction. Polygons, why do we want to compare these to networks or even consider them as networks? Because we can, in many senses, think of inside, obviously we can think of inside and outside of a polygon. And so the inside might be defined as being that part that is to the right of the line in its direction of construction, or to the left of the line, or however we're going to define these things. There tend to be standard ways of doing this. But it also helps for storing information if we only have nodes stored, knowing how to go from one node to another to build up our polygons, simplifying our data structure. So we can use this Polygon Arc Topology. So if you, for example, if you want to build up polygon B, which is this one here, we're going to construct it from a series of arcs. Now, arcs is just another way of describing a line. Number 1, going all the way around there. Then we want number 6, we're going against the direction of travel there, but that doesn't matter for now. And then 8 goes around there, and then 5 is that arc there, and then we're back to number 1. So we've created this polygon. C would work similarly, not bother with the details. But we can also describe the arcs by saying which polygons they have to their left and to their right. So if we look at arc number 1, which was this one here, we have this polygon outside is A on its left. That's its direction, it goes that way, and polygon B is to its right. With let's take another one, let's take F down here. So F we have down here, and we've got starting the counting at 8 there, so that's that arc, and then we go to 9, and then 10 goes around there. And then we have, what's going on here? Well, we have this hole in the middle, you see. So we have this indication that there's something else going on, that we have to cut out a hole, and that's defined by one single arc called 7. But if we look at number 10, the outer definition of number 10, we have what's going on for this arc here. We have D there, we can see that going around there, to its left because the arc is going that way, and on its right we have this F. Ways of encoding information about our polygons and about the arcs or the lines that construct them, that build them up. This is technically doable. You will hopefully have an exercise soon on how this will become applicable. Another way of looking at networks, which should be familiar from previous courses, is just going from node to node, where we construct an arc by saying this is our basic structure, and this is the arc node topology, and is hopefully more familiar from network analysis. Start here, go there. Stop there, go there. Very basic, and it's encoded in a simple table like this. And then the nodes, the coordinates for each node are stored somewhere else. Vectors also have to store more complicated information about structures. For example, curved structures. We were looking at arcs there. Well, that was fine. That suggested some sort of curved line. But how do they do this? Well, there are a couple of main, three sort of main types, we can say. If we look at these, the left-hand example and the right-hand example, which aren't covered in these red dots, there's the circular string and the Bezier curve. Now, these store information whereby we have three, in the circular string we have, in this case, 3 control points, and then there's a geometric description saying curve around to connect all 3 of these points. Take the arc that fulfills the criteria. This is the start of the arc. You have to pass through this point and then finish at that point. And there's only one arc that can do that. The Bezier curve says start here and then leave that point going along in that direction. And you're going to go to that point, but you're going to approach that point coming in from this direction. So you're going to go around and come back into there. So we need to store information on these handles as well. Where are they? These can be diametrically opposed, or they can actually be free to move independently of each other. And the length of these handles determines how strongly this arc is bound to following that curve. If the handle is very, very short, that's pulled into there, then it doesn't really follow that line particularly strongly. It can come in, this would curve around more like that. If we draw it out quite far, then it's instructed to follow that strongly in and sort of make a tangent along that line as much as possible. These are relatively complex constructions, and many formats don't support them natively. You can draw using these methods, but then when you save the data, it all just gets compressed down into being a string of straight lines. This is typical for, say, the shape file. That doesn't handle either of these. You can certainly construct them using these methods, but once the data is stored, it will just be a series of straight lines. Some, like the geodatabase in Arc, that can store Bezier curves and splines, for example, in them, so that this geometry is actually stored directly in the file rather than just ending up as a string of straight lines. What do our vectors look like? So we're going to do this comparison again. If you remember, previously we looked at a text file for a raster, and in previous courses you have hopefully at least looked at the GeoJSON format. And we can see that we get a lot of text. We've got because of the nature of the vector format, we tend to have our metadata in order for this to actually work. And we can see here in this GeoJSON format, we've got, okay, we're going to start opening a thing. This is a thing. This is a format that doesn't follow our relational table, relational database construction at all. Rather, this is one of those more open formats where nothing is related to each other across tables, but rather we construct objects and we have to open up the object and then close the object afterwards, and anything defined within it belongs to that object. So here we open up a feature collection, it being opened up here, and then here we're going to start some features, and it's going to be a list of them. And we looked at this in a previous exercise, and we get this long string of data. This is a text file, and here we can see that we start getting some coordinates in here. Here we actually start building up a polygon. Oh, right, okay, so, and that goes from one point to another point. We can see this is two-dimensional. There's no Z coordinate here. I'm building up a long list of things. Well, that's the GeoJSON, and we can read it, we can interpret it, and it's a very common format, very functional, absolutely, definitely worth knowing as you get more and more into GIS. But it's actually, to my mind, and in terms of a text format, it's useful because it's used all over in many different tools, and it's used on the internet and for different web services. But something that's more useful for us when we're working with, if we're actually going to have to manually enter data into a text file, then a format that I like, which is not commonly implemented, unfortunately, is the GMT format. Now this provides us, we start up in our header here with a text file that says this is going to be a multi-polygon. So we're going to have a polygon file that can have multiple polygons as an object. And then we have a bounding box here for our data, and then we have, this is an EPSG code for our coordinate system, and then we've stated this, and then we actually define the coordinate system here as well. We describe it more and into even more detail, and then we have down here we start to define our table, our database, and here we have our column headers, and here we have the types that are going to be. So these are equivalent to each header it tells us what they're going to be stored as, whether it's going to be a string or a double, as in a number. And then we say, right, okay, that's what the headers are going to look like. Each point has a row in the table, and the table is going to look something like this. And here come the features. So our header is this big long thing here, right? Okay, and that's actually the definition of the coordinate system, taking up so much space. But once we've done that, because the coordinate system is actually quite complicated, here we have our table definition, and then here we have an object, and its information in the table looks like this. So it belongs to this particular river here, and we have some information about, we can see its area in 1973, its area in 2001, and its area in 2008, and so on. And then we start defining the nodes, describing this. This is a glacier. So this is a quite convenient way, I think, more convenient than the GeoJSON. Even though GeoJSON is good, like it, fine, definitely use it. But if you are looking at entering in vector data manually, I think the GMT format is a lot easier. Personally, I find this a lot easier to deal with, because once we've constructed this header, then we just want the table data and then the coordinates that we're interested in, and we just list them. We don't have to construct, we don't have to have this opening and closing of brackets and creating lists and all that sort of thing. It's just here, it's nice and convenient, human readable stuff. I think the GeoJSON was human readable, but not a fun read. It's not going to be a bestseller. Well, this is either, but this is at least easier to use. So to summarize again, pros and cons of the raster. We have this nice simple structure. We can work with continuous data well. We can do certain analyses are very easy to do in raster format. And essentially for remote sensing data, there's no alternative. It's just the best way to work. But we can end up with unnecessarily large data storage because of having to store, especially in class data, just empty stuff that we're having to say nothing here, nothing here, nothing here. And because we don't actually store objects, we're not storing things, we're just storing these implicit collections of cells. We don't really get to we don't have, things don't know that they are connected, they don't know that they belong to each other or have a relationship to each other. We can't have topology, not really. So it tends to be bad in that sense. So network analysis isn't going to work, or any other topological analysis is really not going to work with raster data. We really do have to convert to vector, where the vector has this great quality of only having to store the information that is needed. It doesn't need to worry about what's not there. Where there isn't stuff, it doesn't care. It doesn't need to do it. But also we have this very high precision, but also we can potentially have very high accuracy if we've actually gathered information in with high accuracy. Whereas the raster data, we can have high precision potentially in our data storage, but it might not be terribly accurate. The vector can also store several qualities about an object or a position in space. A lot of information, and flexibly as well. The object next to it doesn't have to have anywhere near as much information, and then we save space. Whereas the raster, we have this problem of always having to fill every single raster layer, even if it's with no data, no data, no data. So these are the basic qualities of raster and vector in a GIS and remote sensing context.